Okay, some quick administrative stuff before we get started. So my office hours are going to be on Fridays at noon. So that's posted on Canvas, and it'll be hybrid. So you can either come to my office or you can Zoom in. And then Trisha, do you have
My office hours are on Monday, next week. They are on Monday. They'll also be hybrid, but email me if you want to do Zoom because my battery is not super great. I'm not going to leave it open until then. I'm not going to open it until someone tells me to say you want to. And then it's going to be 17:15. It's going to be West Village. The room is on campus and it's like on Hilliard Street.
Yeah, my office is in West Village. You can see the address on Canvas as well. So couple other things. So if you haven't looked, so I do provide class resources. So one of the things is each lecture has an accompanying set of notes with it. So that's all available on Canvas. So for example, like this. This is the set of notes accompanying like lecture 1. And so all the lectures will have notes with them. So if you miss anything, it should all be there. The lectures, as I mentioned, are recorded. Although last lecture's recording got corrupted, so we won't have that up, but hopefully for the rest of them, it'll be smooth sailing. And speaking of recording lectures, I mentioned last time that I will occasionally be out of town. So one of those days is actually going to be next week. Next Wednesday, I'm going to be out of town. So what I'm going to do is I will record a lecture on Tuesday night. And that is optional for you guys to attend. But if you want, you can do it live and then it'll be recorded and posted. Okay. So I will post all of that information on Canvas. All right, so today we are going to get started learning about regressions. So let's go ahead and draw a little graph here. We've got our x-axis and our y-axis. And I'm gonna draw a couple points down on here. All right. So I would like a volunteer. Who wants to draw me the best fit line that they can do? All right, give it a shot. We're gonna have we'll have a little competition here. Oh, okay. All right. Okay. Anyone else want to give it a shot? No. All right. Give us a line. All right. All right. Anyone else? Anyone else want to give it a shot? All right. Give us your best line. All right. Yeah. Cool. Okay. So we'll why don't we put it to a vote here? So raise your hand. Who thinks the red line is the best line? Yeah. A couple. How about the yellow line? A couple more. And the green line. Okay. And a bunch of people who are abstaining. All right. So there's no right answer here, right? Or not necessarily a right answer. So why would you vote for one line versus another? Yes.
Know what you're measuring, you should know something about like the physics of it and maybe a linear system and then should be the linear like fit if we're assumed to be at least close to linear.
Okay. So we're talking about kind of the shape of the line. If you have some intuition about like what you think that shape should be, that can help inform how you draw it. Yeah, certainly. So if we were thinking about like a strictly sort of linear system, would the yellow line be better or would the green line be better? Assuming these are both just kind of straight lines. What do you guys think?
Green,
The green? Why?
it seems to better fit the observations.
What does that mean, better fit?
So this X is on the plot right there.
The dots, yes.
Yeah, it's passing almost as close as three of them.
Okay.
The yellow line seems to be passing to two of them and missing one of them.
Okay, but by that logic, the yellow line is also closer to this, and this than the green line, right?
From eyeballing it,
Well, I mean, I can tell you for sure that the yellow line is closer to these, right?
Yeah.
So, yes.
The distances from the line to the observed values and the see which one has the minimum.
Yeah, okay. So now we're coming up with like a quantitative criteria for kind of determining if this one is better or if this one is better, right? You can look at distance. Yeah, well, so, okay, but so we had a sort of cheeky line over here. So technically, if that's the criteria that we're going to go for, then the red line is better than the yellow line and the green line, right? Yeah.
Like a subset of the data, and then the red line might not actually be.
Yes. Yeah, exactly. And so if you were just to look at this data, you may come to the conclusion that the red line is the best one. But I think the point that you're making, and maybe the point that I'll try and exaggerate here, yeah, so this red line it's actually kind of missing that one over there, right? So let me try and do a better job over here. So I'll go like that. Okay, so this line goes through all of the points. But so does this one. Okay. So looking at the sort of, if we call we're gonna call the distance from my line to any point like a little error, and then if you sum up all of those errors, that gives you kind of the total error of your line, right? And so my blue line that I just drew over here has an error of 0. But so who thinks that that is the best fit line, this blue one that I just drew? No? Yeah, and so the point that was being made is that let's suppose that this represents only kind of a subset of the data, right? And in actuality, let's say I left out a point right here. So now you've got this giant error term going all the way down here, whereas it was relatively close to my green and yellow, and actually pretty far from the red as well, right? And so that's a principle, that's actually one of the biggest principles that we'll be taking advantage of in this class in thinking about sort of the error term as it relates to any of our estimates. And so this is something, right, that wasn't, that we didn't use to train our lines, right? A training set to determine how we drew that line. And so this is called an out of sample point. And so we'll try and leverage things like out of sample data in order to sort of validate our lines that we're drawing or our fits. Do you have a question or
Yeah, I
comment?
guess also like roughly thinking about the uncertainty of each of these points.
Yes.
So like some of them could be more certain than others, and that would might influence the best way of like, you know.
Yeah.
analyzing
Yeah.
most of them, but I'm not sure that's something we get to super soon, but.
We'll talk about that. Okay. So let's get rid of all these guys. And actually, let me go ahead and get rid of this. Okay. So, well, actually, I can't use that. All right, let me go back. Okay, so we are now talking about making some objective measure of our fit. We are going to mainly be starting in sort of the linear space first. And as the quarter goes on, we'll start to delve into sort of more complex nonlinear systems. But so presuming that we are mainly talking about linear fits right now, essentially, we have kind of devised this way of doing an objective measure of the best fit. So in that like green versus yellow line, we can actually try and figure this out, right? I can look at the distances from each of my points to my line, right? And if this is a error term epsilon, I can leverage this in order to figure out which like straight line is the best, right? So more specifically, does anyone have an idea of how I would leverage each of these error terms? Like what is one way that you could do it? Yes, so I could add all of these up, but there's a little nuance to that. So let me see if I can demonstrate that really quick. So let's say this is +5, -3, -2, or sorry, -3, -2, +1, +1, -1, -1. So if I added up all of these errors, 7 -7, so it would have the error of 0, which is not quite what we want, right? Because they're like canceling each other out on both sides. Yeah. So yeah, so you can square it. Yes. So okay, hang on. So this is, if you square it, this is known as an ordinary least squares regression. That is right. So least, you're trying to find the line that reduces the error as much as possible. So least, and then you're squaring it. So this is the OLS regression that you may have heard of. So you could also take the absolute value. That is a perfectly legitimate way of doing this. Why do we do a least squares instead of a absolute value normally? So who's taken like classes on regression before? Anyone? A couple people. And so OLS is by far the most common way of doing linear regression. So why is that? Why don't we do absolute value? Does anyone know? So it turns out that the solution to this problem, this kind of optimization problem, back before we had good computing power, right? So this type of approach was first derived in like the 1930s. It's actually way easier to do this analytically when you square it compared to when you do the absolute value. And so that has kind of continued on as a, I don't know, like tradition, or not, maybe not tradition, but you know what I mean. Even though computers can do absolute values and solve it just fine. Right? So little bit of historical context for that. All right. So what is the equation of a line? Anybody? Yeah. Oh, yes. No, there will be a difference. Yeah. So that the yeah, actually that's a good point to think about. What with the if you summed up the squared errors versus if you summed up the absolute errors, right? What would that be in this specific example?
So we call 7 top and bottom.
So, well, this would be 1 squared plus 1 squared plus 5 squared plus -2 squared plus -3 squared, right? And so on and so forth. So if you add all of that up, 25, 27, 31, 33 plus 9, so 42. Whereas the absolute value error would be 14, right? So in an ordinary least squares, the line here that you're making will penalize points that are farther more than an absolute value one would. And so the lines could, in theory, well, in theory and in practice, they will be different, right? Which is, partly why, when we're talking about that like green line versus yellow line, there is still some subjectivity to that, even if you're thinking about this quantitatively.
So, OLS or penalized points that are
Farther from your fit. Yeah.
it won't as much, and it would be better to use that value. It would treat them all more equal.
No, that is a subjective decision, right? Like there's deciding to penalize points that are farther from your line is that's not like a quantitatively better or worse, right? It's also an analogy would be like the criteria for throwing out an outlier, right? So you may have good reasons or bad reasons for doing that.
When would we always use OLS, or are there instances in which we use an absolute value approach?
I mean, OLS is kind of the gold standard for these things. So yeah.
Would there just be one line that minimizes some of these squares, or would there be others? So if there's another line.
No, there's only one line. There's always yeah, I don't remember that proof anymore off the top of my head, but there's one line that will do it. Yeah. And in fact, if we know that the relationship between X and Y is linear, there is no better estimator than your OLS.
So there cannot be another linear relationship that, let's say in the red line's case, but if there's another line that's getting closer to the points below it, but farther away from the ones above it, would that not?
That would be talking about a different criteria than squaring.
Okay.
Yeah. Okay, so I want everyone to dig real deep here. Back to your 9th grade, 8th grade. So what is the equation of a line?
Y is equal to mx plus c.
Great. Y equals mx plus b. Okay. So y refers to points on this axis, x refers to points right on this axis. What is m and what is b? Slope and intercept. Great. So everybody knows this. And in the regression world, we use this exact form, except the parameters are just slightly different. So most commonly, you will see this being written as y equals beta x plus alpha, or something like y equals beta 1 x plus beta naught. Okay, but it's the same thing. Your beta refer to your slope, and this alpha and this beta 0 are just your intercept.
Question on the equation, wouldn't the y have a hat on it to say it's?
Yeah, we're getting there. We're getting there. Yeah. Okay, so hats. There's a little hat. What is that? What are we talking about here? So this is generically the equation for a line. But if you are talking about specific points as it relates to the line that you've created or to the data that you're referring to, you will also see this sort of nomenclature or notation. Okay, so yi is equal to beta xi plus alpha plus epsilon I, and y I hat is equal to beta xi plus alpha. Okay, so what are these referring to? So yi and xi are the points in your data. Okay, and so in that graph that I made, here, like this. Each of these points, so this could be your x1, y1, x2, y2, x3, y3, so on, right? So in order to get to the actual point yi, you'll notice that if I just take this here, my beta times my x point plus my intercept, that will land me. So if I plug in x3 here, that's going to land me on the red line and not on the x. Okay. And so to get to the x, I have to add the error term that's corresponding to that data point. And so once I do that, plus epsilon I, now I am at yi. Okay. And so the difference between yi and yi hat is this is your actual point, and this is your fitted point. So the hat refers to the fit. So this is actual, and this is the fit. All right, any questions about this? Great. So how would I go about actually sort of solving for my beta and my alpha, right? Essentially, there are two methods for doing this, or two kind of approaches that we can think about. I can essentially do a smart version of guessing and checking, right? And so I can like move my line up and down and kind of wiggle it until the sum of my squared errors is as small as possible. Okay. And that refers to a set of numeric methods. So if I want to do calculating coefficients, we're calculating the values of beta, comma, alpha, you have numeric methods, which I would refer to as like a smart way of guessing and checking. The other way is analytical methods. And you can think of this as actually kind of solving the equation. And so this optimization, right, of minimizing the sum of my squared errors is actually a very well-known problem that was solved quite a long time ago. So this is a solved optimization. And the solution for this is beta is equal to, if you arrange your x's into a vector for 1D or matrix for multiple x's, it looks something like this. So your beta hat, we'll say, is equal to x transpose times x, the inverse of that value, times the x transpose times y. And if you do this, this is going to get you your betas. So we're not going to derive this. That would be in a more sort of fundamental regression theory-based class. We're doing applied. So one of the things to note is that when you when we run examples of this in R, when you're doing linear regression in R, this is what's happening behind the scenes in order for you to get your coefficients. Okay. The numeric methods, the way that you would do this is an optimization procedure called gradient descent. So this is solve for beta iteratively by guessing and checking. And so this procedure draws the line, and it'll get closer and closer and closer to your sort of solved optimization. Essentially, you say stop when there's like a threshold for your error that it's like small enough that you're happy with the answer. So why are we even talking about gradient descent, right? This seems way better. And in fact, this, right, as I was saying, in most sort of procedures, you're going to be doing this type of operation. However, we are actually using gradient descent more and more these days, especially once you're talking about trying to do regressions on really large data sets. And so machine learning has actually reverted back from this to this. And the reason for that is that this operation here, doing an inverse of a matrix, is actually very memory intensive. And so if you are trying to do very large scale regressions on thousands and thousands or millions of variables, it turns out that the memory requirements are beyond a lot of like traditional computational resources to do in like a reasonable manner. And so actually gradient descent is going to be substantially faster and more efficient than your traditional analytical methods once you are reaching a certain scale of data. So we're not actually going to be really doing this at all. We're not getting to that kind of size in this class, but I do want to note that for anyone who might be using, you know, really large scale data sets and trying to do linear regressions, you're going to want to look at doing something like this. Okay, any questions? Yeah.
Can you X transpose you said about this?
Sure. So this is a matrix. It is It is a matrix transpose. So let's say you have something like 1, 2, 3, 4, 5, 6. This transpose is equal to 1, 2, 3, 4, 5, 6.
Right.
Yes. All right. So why don't we jump on over to our studio and take a look at doing this. Yes.
One question, the equation for the coefficients and so, do we make any of those assumptions to derive those, such as the conditional mean, the other term assumption and other stuff, and do we need to get into that for any of the analysis?
Yeah, I'll talk a little bit about that later. Yeah. Yes.
Is that same number of words, is that just for linear bits, or is it then also multivariable?
Yeah, so any OLS, so including sort of multivariate. Yes, for the, are you talking about the analytical? Yeah, the analytical solution is specifically for generalized linear systems. So you can do many variables with that. All right. I can find my mouse. All right, here we go. So we are going to make an artificial data set. So the first term here, I'm going to generate 20 random numbers. So the nice thing about kind of generating this example myself is that I can do something that you traditionally wouldn't really be able to do in the real world, which is I can actually know my true relationship. Okay. So I am creating a y's, which are random x's times 0.5 plus my deviation. This is going to be my error. So I'm artificially introducing noise, error, which is, maybe we probably haven't talked about this. So R norm is a function similar to R unif. So R unif, as a refresher, that is a random uniform distribution. I'm just drawing 20 numbers out of a hat that's between 0 and 1. R norm is a random normal distribution. I am drawing numbers out of a hat. I'm drawing 20 numbers out of a hat, out of a normal distribution set of numbers that has a mean of 0 and a standard deviation of 0.1. Okay. So the nice thing, again, going back to this, the nice thing about this particular example is I can run a regression on this, and then I can see how well it does compared to what we know to be the true relationship, which is x is half of y. Okay. So what does this look like? Actually, let's see. Yeah. If I run all of this, I can jump on over to my plot. Make this a little bit more. Okay, great. So I've got a jumble of points in here. The trend kind of looks like this. And actually, I am going to throw all of this into a data frame. So this will make a table with 20 points that you can see here. And these are just the points here. So the way that we run a regression, a simple linear regression model in R is using a function called LM. So I'm going to call the object example model, and I'm going to use this function LM. LM stands for linear model. And so the way that you do this is you say Y regressed on X. And I guess let me reiterate that because this is a common source of confusion. The way we describe Y equals beta X plus whatever is that you say Y is regressed on X, not X is regressed on Y. That's actually a common source of confusion on some of the homework, so remember that. And then I will pull that data from the table that I just made. So when you're doing these regressions, these are referring to the column names of your data set. Okay. And you don't need to put quotes around them. It will just know. So I can go ahead and run this regression. And the best way to kind of view the results of the regression is using the summary function. So I'll just do summary of this. And we can see the regression table, and we're gonna kind of work through all of this in a little bit. But the main thing to know right now is that where it says estimate, this is referring to the values of your parameters. So for X, so this is the parameter related to X, right? In our notation, this is our beta, and our intercept is alpha. So what is the true value of beta and alpha? 0.5 and 0, exactly. So this is saying it's about 0.4, and this is 0.04, okay? And don't worry, we'll get to all these other values and kind of get an understanding of what that means in a second. Go ahead.
If we then drop around regression that drops the intercept, would we get something that aligns more to our original setup of y is equal to x times 0.5 plus deviation?
It's possible. We can try that. Where is my mouse? Does anyone know how to get rid of the intercept? Yeah, -1. So if I put -1 here, it will run the model assuming no intercept. And in this case, you do end up getting closer. But what I will say is that you typically ought to be careful when you're doing something like this. You presumed no intercept because we know the true function, but in reality, you won't know the true function. Yeah. Sorry, the what? Yes. So yeah. So if our equation is y is equal to beta x, so we refer to the outcome as the response variable, and we refer to the sets of variables that are leading to your outcome as the explanatory variable. So I will say that another common way of referring to this is a dependent variable and independent variable, which is, don't use that term. They're all wrong. Well, they're not wrong, but it's a bad, it's actually, when we think about what that means from a statistical sense, which is really a lot of what this is, it's not, doesn't really make that much sense. So, you know, people will use independent and dependent variables, but I think that they're all wrong. So this would be your dependent and independent variable. So in your function, essentially what you're doing is the way it works is you have your response variable tilde explanatory variable. And so this is the first argument term that you would put inside of the function. We will get to multiple variables later, and we'll see how to do that. Yeah, so I usually don't teach this, but someone asked. So when you run a linear model, it will automatically put in an intercept, that alpha term. If you have a strong reason to believe that there is no intercept, you can put -1 here to get rid of the intercepts. Yeah. Yeah.
So like, behind the scenes, I suppose the minus, it assumes that the intercept
Is 0.
is 0.
Yes.
Straight, okay, so it always assumes it's running through 0, so you minus going the other way.
Yeah. Okay. So let's go back, grab this guy, and we can see what the fit is. Oh, whoa. I think that's new. That's kind of cool. It usually doesn't change the color. Well, I don't use RStudio, but this is new this year. Cool. Anyways, boom. All right, so there is our line. So AB line, you can just put in the model and it will put in the best fit line. Great. Any questions about any of this? Yeah.
So is this a bit different from the ggplot package where you have to attach the line as a plus? But here you can just put the plot command on a separate
Yeah.
line.
Yeah.
Does it seems that they're together?
Yes. You can just like keep adding elements to the chart. Okay, I will from now on, from next lecture on, I will do my best to just do everything in ggplot because base plotting sucks and you shouldn't use base plotting. So I will practice what I preach, but for today, I'm not gonna do it.
But you have to run these together for the line to appear into the plot. You can't run them
No. No, I can run, I can put more things into this if I wanted, AB line, or,
Literally saying all the elements get added to the plot command at the top.
it just adds it to the last thing you plotted,
Okay.
which is also dumb.
Yes.
Okay, so, let's see. Is it A or B? I can never, oh, H. H equals 0.2, color equals blue. So cool that it lights up like that. All right. So you can see, like, I can now execute this after the fact and it'll not do it. Or is it V? Okay, well, let me do, I'm pretty sure V line works. No, all right.
Let me start on them together.
All right, no. AB line, I can do this. A is the intercept, right? Yeah. Okay. Uh, oh yeah, B equals 1 or zero. Okay, wait. B is the intercept. This, okay, like this. Cool. All right. I don't know what I made, but I just added a line after the fact, right? Okay. Anyways,
H line with that.
I'm pretty sure it used to be.
I looked at the help and it's like, no documentation. Just
Okay. Well, this was just to prove the point that base plotting sucks. All right, great. So let's actually jump back to the notes for a little bit. Okay. Great. So everything that we work towards is about sort of figuring out how to generate that fit line and then programmatically doing that in R, right? And again, the way that it did that behind the scenes was that XTX inversed XTY equation. However, let's think about this a little bit more carefully. Let's suppose that I've got two fit lines that are identical. We've got one here and one, okay, hang on, I can make that closer. There we go. Okay, so these two lines, let's say, are exactly the same in terms of their slope and their intercept. Now, let me retroactively put in points that were used to calibrate these lines, okay? All right, so if I were to run a regression on both sets of points, you would end up generating the exact same line. But there's something different about these, right? And so what do you guys think? What's going on here?
Is it the R squared?
So we will talk about that in a second. But let me phrase this, or let me prompt you guys a little bit more. Which line do you guys believe more? the left one. And why is that? Yeah, yeah, exactly. And so you can think about this in terms of like a confidence of our fit. Okay, even if the fits are actually the same. And in fact, one way you could even think about this is like if I were to like remove one point, or if I were to remove this point, like which one would get changed more? Which line would get affected more? The one on the right. And so that that essentially implies that we are sort of less confident about the exact nature of this fit compared to the exact nature of this fit. Okay, yeah.
When, in that example where removing one gets better from the other, is that if the line changes substantially, or if the line changes at all, does that indicate that our assumption of the type of relationship, like linear versus something else, is incorrect?
No,
No.
no. We'll think a little bit more carefully about the structural fit assumptions a little bit later. Okay. So this is all kind of in the reference to and in context of something known as your standard error. So it's essentially this concept of like, how confident are we that this line is like at what we decided it is, right? And so if we think that this line wiggles only a little bit as I take out points, then we would think that this line wiggles a lot more as we sort of take out points. And so the standard error is essentially what helps us capture the uncertainty of this line that we've come up with. All right, so I will write the mathematical equation for a standard error, which you can see once and not really have to care about because no one derives these by hand, right? Except in classrooms, but not in this class. But, you know, it might be useful to know. So this is the sum of yi minus yi hat squared over n minus 2 divided by xi minus x squared. Okay, so a common another common mistake to make here is to think about the related term of standard error, which is a standard deviation. And so these are two different things, okay? So standard deviation is data deviation from the mean, whereas a standard error is how precise is our estimate of the mean. So if this line represents the mean value of the fit, these models tend to assume that that the distribution of possible line values here follows a normal distribution. And so the standard error is going to give you, so let's say this beta is equal to 0.7, the way that we think about the standard error is in a distribution like this. So if I have a distribution with a mean value of 0.7, if the standard error of beta is equal to, let's say, 0.2, then if I go up to 0.9, or if I go down to 0.5, that would encompass a set of lines within one standard error value. Okay. And so in a normal distribution, does anyone know what percentage of the? Yes. So within not standard deviation, standard error. So it's about 68%. So 68% is one standard error. And then 95% is two standard errors.
So would this then extend to saying that within some confidence, you can say that the values of the beta coefficient are within this range?
Exactly. Yes. So let me see. Do I actually talk about this? Yeah. Okay. So when we talk about has anyone heard of like statistical significance? Yeah. And so do you guys know what that means in reference to this? Yes.
That the beta isn't zero, essentially?
Yeah. So the test here is that some percentage of the time, right, we think that actually the slope might be so on average the slope is 0.7, but some percentage of the time it's 0.5, and some percentage of the time it's 0.9, right? And the question as it relates to a statistical significance, which is a term that you hear all the time when people talk about regressions, is whether or not this line here, how often is that line flat? And so what does it mean for this red line to be zero, like qualitatively, if you think about it? Yeah.
Means the intercept is explaining the data value is better than any lines.
Close, yeah. Yes, so if this is flat, it means there's no relationship between y and x, right? Because my x can change all it wants, but nothing in y changes. So qualitatively, if we think about what that means, is like you're trying to come up with a model where you're determining some relationship between x and y, but if there is no relationship, well then, I guess, well, some people will say the model is no good. I don't think that's quite the sort of right interpretation. It just means that there's no relationship. And so this like standard test of significance is doing that. And so let's say, how often do we think that the value is actually going to be zero? In other words, that there's no relationship. And so using this sort of normal distribution, you can say, well, it will be zero like less than 1% of the time, or less than 5% of the time, or less than 20% of the time. And so we as a society have decided that less than 10% or less than 5% or less than 1%, depending on the context, constitutes it being good enough that we think there's a real relationship, right? But these distributions are sort of naturally an artifact of your data. And so, if it's the case that like we've decided that 5% of the time is good enough to qualify there being a relationship, So we'll try and blow your minds here. That means that 5% of all scientific studies doing these sort of regressions are probably falsely attributing a relationship, right? Because that's just how, that is literally just how statistics work, right? So take that for what you will. Okay, am I confusing anybody, or does anyone want any sort of more sort of clarification on this? And we'll try. We're gonna, when we go into the code and we look at this again, I'll try and talk about this again in the context of the example. Yeah.
From analytical standpoint, when you're trying different data, are you then trying different lines essentially to see?
Yes.
So the model will be drawing different lines and it's.
And then wait, what do you mean in an analytical? In an analytical, you just get the right answer. In a numeric, you're guessing at the
Okay,
lines.
so-
Yeah.
So in a numeric method, then it's trying different lines.
Yes.
Different betas?
Yes. But it's like trying it in a smart way.
Is it trying to, when it's trying different lines, what does it mean? Is it trying to minimize that?
It's minimizing the square of the sum of the squared errors. That's it. It's an optimization essentially, right? Where you minimize sum of squared errors subject to changing your beta, changing the slope.
Okay, so for a given distribution of X observations, it's trying different predicted lines.
Yes.
Okay. Yeah.
Exactly. Okay. So yeah, what we're trying to do here is like build ourselves ground up to get an understanding of all these things, and also try and get exact about how to interpret a lot of these like validation methods, and like what does a standard error means, what does this statistical significance mean, because when people do regressions, these are common things that people talk about as a measure of how good a model is, but that is not what these things are referring to, right? These are referencing exact things. This is just talking about our distribution of our estimation. And so another common one that we talk about in terms of about thinking about whether or not a model is quote unquote good or not is R squared, okay? And so let us hone in and talk exactly about what that means. So R squared is the coefficient of determination. So all this does is it answers this question of relatively how much variation is captured by the model. So R squared, I will write out the equation, which again, you don't need to memorize for any of our purposes. So this is going to be 1 minus the sum of my squared errors, right? So we should get comfortable with this kind of term here, right? So this is my actual minus my, so my actual observed points versus the fitted points. Take the square, those are the square of all the error terms, right? Divided by the square of the difference between my actual points and the mean of y. Okay, what the heck does that mean? If I draw a graph here, so y, x, like this, da, da, da. And I'm going to duplicate that over here. All right. Essentially what the R squared is doing is it is comparing if I just had the average of my y's, right? So you just add up all your y's, divide by 6, and you come up with a flat line. Sorry, that looks a little bit tilted up. Hang on. So there. All right. So it's essentially asking how much better is this compared to this, okay? Because this is saying if I had my best guess as just the average of the y's, would my model actually be doing a better job at guessing those points? Would the errors be smaller? And so this term is most typically going to be between 0 and 1. It's one of the big reasons why you hear about R squared all the time, and R squared is like one of the gold standards of reporting a good the goodness of a model is because it's standardized. So across different types of models, right? Any data set, any model that I'm running, my R squared value is going to be between 0 and 1. So 0 means that less of the variation in the data is being captured by the model, and 1 is saying all of the variation in the data is being captured by the model. And again, if you hear people say like, oh, my model is amazing, it has an R squared of like 0.9, that doesn't really mean that the model is actually good. It just means that maybe the variation is getting captured, right? But there are lots of other things that we need to think about in terms of what sort of constitutes a good model. Yeah.
Is there one minus term? Is that the minus term? Is that the portion of variation being explained by the error terms?
No. It is referring to the proportion of the error here divided by the proportion of the error here. And so basically, the better your model is, the smaller this term will be, right? And so the smaller this term is, then you're doing 1 minus a smaller overall term.
And that's the error term, yi minus y hat I? Or is it the opposite?
This is your SSE. This is your sum of squared errors. Yeah. And I'll also say for nomenclature's sake, so errors are often also referred to as residuals. So when we say an error or a residual, that is essentially the same thing. It's that distance is the residual. Okay. Okay. So R squared tells us a standardized metric of how much variation does our model capture compared to just like averaging everything out. Okay, let's jump back to R. All right. So let's kind of replicate that idea. I'm going to make y2, which is going to be x times 0.5 plus deviation times 2. Oh yeah, question. No, okay. So basically, I'm going to increase the size of my error terms. And if I just quickly plot that, we can see everything's kind of blown up a little bit. And let's make a new table so I can run a different regression. And then we will take a look at the results. Okay, so I'm gonna go ahead and make the data frame, run the model, and then look at the results. So if I look at the size of my standard errors, they will have increased. So those are 0.13, whereas the original one was 0.092. And that is, again, an artifact of this. So we're basically doing an empirical example of what I had shown on the board, where as the points get farther from our best fit line, the standard errors are increasing, indicating that the confidence that we have in the exactness of this value is smaller. In other words, the distribution of possible slopes that we would expect is larger for this. So now we can actually interpret the rest of this table. So these are the standard error values that sigma term that I gave the mathematical formula for. That is how you would calculate these standard errors, and you can calculate it manually yourself if you want, and you should be able to get the exact same answer. The t-value and the probability here, which is how we derive statistical significance, refers to that idea of how often essentially that slope of 0.3 is equal to 0. And so given a mean and a standard error and assuming a normal distribution, the t-value tells you how many standard errors away you are from 0, right? And so if you take 0.18531 and you multiply by 1.689, that will equal your coefficient, okay? And this tells us how often in that distribution our slope is 0 or lower. And so 0.108, so 11% of the time, we would expect this value to be 0 or less. So do we have a good model? Yes, no. Well, according to the standards that we use, this would not be good because it's bigger than 5% or bigger than 10%. And so we would, if our hypothesis was that there is a statistical difference between X and 0, we would reject that because this is larger than 10%. So always think about kind of what that means when someone says a term is statistically significant. Yeah. Yeah, we'll talk about that a little bit later. Yeah. So the r squared, so forget about the adjusted, we'll get around to that. this is the R² value. This is capturing 14% of the variation, whatever that means. And actually, to kind of just demonstrate the sort of nature of that, let's do this. Any other questions about this? Yeah.
18 degrees of freedom for the residual standard error, is that? What is that meant to, okay, why 18 degrees, what is that supposed to indicate?
Yeah, so 18, so if you remember in our standard errors calculation, there's like this n-2 term that refers to the number of data points, essentially. -2 for the initial setting of your the points, the minimum number of points that you need to make a line.
Okay, so 18 could be 48 if we chose 50, right?
Yes.
Based on.
Yes.
Are we supposed to get the same values?
No, because we exactly, so the x's and y's are generated randomly. Yep. And so as you do this, you guys will all technically get different ones unless we like set a seed.